If you do, you can just speak up. Okay. Someone says use counting method to find 3 and 5, and then subtract the doubles. Right. Right. So, you want to use complementary counting here. So, what that means is that because it's hard to find the numbers that are not divisible by 3 or 5, you can instead find the numbers that are divisible by 3 or 5, and then just subtract it from 49. So, uh, for for 3, there are 16 of these because, well, the largest multiple of 3 less than 50 is 48, and 48 divided by 3 is 16. And for 5, there are 9 of these for the same reason. And you add these and you get 25. However, remember that you're counting the numbers that are both divisible by 3 and 5 twice. Remember the principle of inclusion and exclusion, which basically says if you have a bunch of groups and you want to find the total number of things in all of the groups, you add the number in each group, and then you subtract the number in two groups in every pair of two groups, and then you add the amount in every pair of three groups, and and so on. So in this case, if it's divisible by both 3 and 5, that means it's divisible by 15. And if it's and for divisibility by 15, there are just three of these: 15, 30, and 45. So you have to subtract by 3 to get that there are 22 um, numbers less than 50 that are divisible by 3 or 5. Does anyone have any questions about that part of the problem? Like, or does anyone just not understand in general how this works? Oh, okay, well, then once you get 22, you have to remember to subtract it back from 50, or 49 actually, because 50, you didn't count 50. I know several people, they forgot to do this and had the answer 22, but uh, remember you have to subtract it back from the total number 49 to get that your answer is 27. And yeah, that's the thing about complementary counting. You are counting the number of things that you uh that don't count, but then you have to subtract from the total at the end. So does anyone have any questions on the first problem, or like have any questions on what they did wrong? Uh, Like, okay. So an octahedral die with 8 faces, with sides numbered 1 through 8, is rolled twice, and the product of each roll of the two rolls is computed. How many of these rolls produce a composite product? And like, okay, many people made a small error in this one that I'll talk about later. But does anyone want to show or want to share how what ideas they had on this problem? So again, with this problem, you want to do complementary counting. I know some people, they just directly counted the possibilities and got, yeah, they directly counted the possibilities and got an answer. But um yeah, you can do that. However, like that's, well, a not negligible amount of effort. So you should instead use complementary counting, which again is finding the number that you don't want and subtracting it from the total. So the total in this case is just 8 squared equals 64, because you have 8 choices for the first roll and 8 choices for the second roll. And how many of these rolls produce a composite product? So if uh okay, so the product of any two numbers is going to have to be is going to have to be composite unless one of them is 1. And the reason behind that is that every non-composite numbers, which are primes and 1, are only divisible by 1 and possibly themselves. So like, for example, like obviously if you have something like 2 times 7, that's going to be composite because you're just multiplying it. So that makes it easy because the number of rows that produce a product that isn't composite is going to be uh, yeah, it's going to be 1. Uh, so let's just count these rows. So there's 1 comma 2, 2 comma 1, 1 comma 3, 3 comma 1, 1 comma 5, and 5 comma 1. 1 comma 7 and 7 comma 1. So all of these have a prime product because you're multiplying 1 and a prime, and we know that multiplying by 1 doesn't change anything, so these are still going to be prime. And something that many people missed is that 1 comma 1 also counts. Uh, yes, in response to some people, 1 times 1 is 1, and 1 is not prime. However, 1 is also not composite. If you remember, a composite number can be divided by two numbers that are not itself, and 1 does not fit that. It's not prime because it only has one divisor instead of two, but it's also not composite. And also, some other people, they forgot, they only counted each of these once, but you have to count them twice because, again, you can roll 1 and a 5, but you can also roll a 5 and a 1. So in total, there are 9 possibilities here, and yeah, you can subtract these 9 non-composite from 64 total, and you get 55. So does anyone have any questions about this problem? I think most people who got this one wrong, just uh, most people who got this one wrong just messed up using the um one times one. Okay, so the third problem is pretty straightforward based on what we learned last class. So I think some people are probably overthinking it. Does anyone want to share how they tried this problem? And it's okay even if like you're not sure if it's correct or not, because it's helpful to see like why it's helpful to see what you did and like how you can avoid that in the future. So so for this problem, you can think of it as having, again, like, remember, okay, so for this problem you need to use stars and bars because you're partitioning several objects into different groups. In this case, you have to put $10 into 3 types of stacks. So again, remember that, like, for example, if you have 3 boxes that represent each of these stacks, then 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 no matter how you put $10 or just 10 objects in general into these boxes, it'll always like work as it'll always like give you something that shows like how to buy these stacks, uh, and it also shows like it also works in the opposite direction. So you can so again another way you can represent this is instead to have the $10 separately, like we're just going to so this stars and bars, that's what we're using. Uh, so we're just going to use here. So these are going to be our stars, which represent the money, and we're going to have two dividers. Again, there are two dividers, not three, because these dividers can go in the outside or in the middle. And if you have three dividers in the middle, then you can see that you're creating four sections instead. So no matter how you place these two dividers, again, it'll always be a valid way to spend your money, because in this case, for example, you have $2 for the first stack, 0 for the second, and 8 for the third, or like 0, like 6 and 4, or 3, 2, and 5, or so on. And you can also see that no matter how you split these, you'll always have, no matter how you split your money, you'll always be able to it'll always be able to correspond to one of these. Like if I spend 4 and 2 and 3, 4 and 2 and 4, you can see how that works. So this is equivalent to putting two dividers somewhere, and because these two dividers can be between the same two circles, then you could think of it as instead having 12 spaces, and instead choosing two of these to actually end up being dividers. And you could also see how this also works. You could also see similarly how this is also the exact same thing. And uh, so, like for example, if I selected just any, like if I just select any positions, it's equivalent. Like if okay, so out of these 12 objects, we'll say we're choosing two of them to be dividers or bars, and then 12 minus 2 is 10, so that leaves you with 10 like stars, and then you can clearly see how no matter how you divide these, you'll always be able to correspond it to choosing two positions for these. So anyway, using stars and bars, like after this is one thing, like unlike some other things where you've had in the past, where if you know, like some of the things, it's important to know why it works behind it. This one, for stars and bars, it's useful in case you have something that's like constrained or like a modification of it. But otherwise, um, you don't need to overthink it. Just like remember that you have 10 stars and 2 bars because there are 3 types and 2 dividers. It's going to be 12 choose 2, which is equal to 12 times 11 divided by 2, which equals 66. Does anyone have any questions about the problems on this page? Like, does anyone not understand any of it? Because I know this was like a hard class, but really said nobody really said any ask questions. So like seriously, if you don't understand anything, then please ask. All right, so on to the second half of the homework. We have a standard six-sided die that is rolled 4 times. How many ways can you roll a 9? So, does anyone have any ideas or on what to do with this problem? Just Okay, so at least one person like understood how this works. So they said 8 choose 3 or 8C3. And that's correct, but again, like why is that the case? So this is again stars and bars because in any in any way where you have like some number of like some numbers like a plus b plus c plus d or whatever, and you know what they add up to, and you want to see how many ways there are for a, b, c, and d, that's always you use yeah that's always going to be a stars and bars problem, and this case is no different. So again, you have to modify, like, you can modify this by subtracting 4 from 9. And what does that mean? Well, you can think of it, again, using the buckets, uh, sorry for lack of a better analogy, by, like, initially putting 1 in here to begin with. Because now, instead of having to add 1 plus 1 or 2 or 3 or 4 or 5 or 6, we have to add 0 or 1 or 2 or 3 or 4 or 5. And that works with stars and bars. And, um, yeah. I guess another way you could think about this is that if you have 9 stars, then if you have to have at least one in each of them, then there can't be two of them in the same like between the same two. Like for example, you can't have both of them here because that would mean that this group has 0. So instead, you could think of it as having to choose three, actually, sorry, of these spots instead. Like there are 8 spots here, and that's another way you can get H is 3. We're just choosing 3 of these to place a bar in. So like, does this other way of thinking about it make any sense? Hello. For people who just joined, we're just going over the homework right now. You can see the recording for like the things from the earlier problems, and especially some things that like are important to talk to like realize, like any common errors that you shouldn't make. So um and again, like you could also think of it this way, and either way, in this case you have 5 dividers and 3 dividers. In this case you have 3 dividers and 8 spots. Either way, you get the total is 8 choose 3, which is equal to 8 times 7 times 6 divided by 3 times 2 times 1. These cancel, so it's equal to 56. Does anyone have any questions about this problem or like anything else you've got over? Yeah. Okay, so for the second problem, uh, what is 10 choose 1 plus 10 choose 1 plus 10 choose 2 plus 10 choose 3 plus all the way up to 10 choose 10? 10 choose 0 plus 10 choose 1. So it would be very hard to do all of these multiplications itself, but addition is easier than multiplication. So remember that we could construct Pascal's triangle by construct these combinations by using Pascal's triangle, which, as a reminder, for any random point here, you could see that it's a sum of the one that's to the top, to the above and left of it, and the one that's above and right of it, and the sides are always just 1. And you can just make this all the way up to the 10th row, and you have 1 10 foot, and this is the 10th row. It's it looks like the 11th row because like yeah, but this is but generally this one is considered row 0, and this was considered row 1, and so on. And the reason why is because that is what actually corresponds to this. So even though like if you count it, this is the 11th row, this is actually the 10th row because you have Tetris 1 and Tetris 2 and so on. But anyway, like you could see this, and you could add these up, and you get that this time is 1024. But like 1024 is equal to 2 to the 10th power, and that can't be a coincidence, right? And it's actually not. If you just look at some of these smaller ones, you can add these up and see that each of these is equal to uh you can see that each of these is equal to 2 to the power of n, where the n is in row. And the reason why, uh, well, there are a couple of ways you can prove this. Uh, Probably the simplest way is just to think of it like this. So consider anything in a row that's not the outside ones. So how many ways is this like added into the next row? It's going to be 2 because you have the one that's down and to the left and the one that's down and to the right. Actually, yeah, 1 is like that too. So you can think of this as having like zeros over here, and that's how you get that this is 1. But yeah, like each number in a row is included in 2 of the sums below it. So like I'm not sure if what I'm saying makes any sense, but you can see that, for example, with the 6, the 7, it like the 7, in order to get the 7, you have to add by the 6, and the 21 is added by the 6. So each of these numbers is counted by exactly twice in the next row. So you can see how, like, for example, the 6 is counted in these, the 15 is counted in these, and so on. And you can see how, like, if this adds up to x, then this has to add up to 2 times x because every number in x is counted twice. Like, does that make any sense? That argument? Uh, like, but another way you can think of it is instead just think of this directly. So 10 choose 1 plus 10 choose. Well, okay. So what does 10 choose 0 mean? That means choosing 0 objects out of 10. 10 choose 1 means choosing 1 object out of 10, and so on. And you're going to notice that we can actually just choose, like, no matter how you choose any number of objects out of 10, it'll always be included in this exactly once. Because, like, if you choose 3 objects, it'll be included in 10 choose 3 and no other one. If you choose 7 objects, it'll be in 10 choose 7 and no other one. So what that means is that we're just looking for the number of ways you could choose any number from 10, and that's just 2 to the power of 10. The way you can think of that is if you consider each item individually. So because you don't care how many there are, because no matter how many there are, it'll always be counted once. Each one of these, you can think of having 2 options. It can either be chosen or not chosen. So, naturally, you have two choices for each of these, and you multiply all of these two together, and you get that their product is going to equal to 1024 because it's 2 to the 10. And like that's another way you can think of it. In combinatorics, there are a lot of arguments like this where, like, instead of trying something by actually expanding out these, or by using Pascal's triangle or something, you instead simply, yeah, you instead simply use the what is it? You instead just think of it like as an argument regarding choosing stuff. And again, remember that we also use a similar argument to prove that these are combinations, which is that like you can single out one object, and if it's in there, then you have how many choices. If it's not in there, you have how many choices, and you add them. So I know that was probably a bit hard to understand. Um, like, does like can people tell me in chat if they fully understand it or if they still need any help or anything? Like, if you do fully understand it, then please like indicate it, because okay, that would really help to see to help people like learn stuff actually. So some people said they sort of understand. If you said that, can you explain like what you don't really understand about this, or like actually anything about counting in general, like not just this, and what specific part about counting is? Okay, you don't get the stars and bars trick. So like, what specifically do you? Oh, like, do you understand at least the concept of splitting a plus b plus c plus d equals 9 into this? Like, do you understand how these two like how, do you understand how this represents one possibility for this one? Okay, and so to find and what that means is that to find like the number of possibilities for this one, that yeah, to find the number of possibilities for this one, you could simply find the number of possibilities for this one, and the and uh, so you can see here that there are 9 dividers, no, 9 stars and 3 bars, for example. So do you see how this represents 12 choose 3? Like how there are 12 choose 3 possibilities for this? Because you can see that there are 12 objects here and you have to choose 3 of them. Okay. So let's instead of setting them to be stars and bars, what if we just set them as like just generic, just like some, I don't know how to represent this, but like if I just have this instead, that's basically what we have. We have just 12 spots. And do like 12 choose 3 just represents choosing 3 of these 12 spots. So let's say we choose this one, and this one. Then what we could do is we could put these bars there, and we can put and then the rest of these have to be stars. Like, do you understand that? Do you understand how like how you're supposed to choose 3 of these 12 locations to be to be bars, and then that okay. Then from there you can see that and this is going to be the same thing because they're always going to have 9 stars and 3 bars, and you can't have the same one. So you add so yeah. So you get them, and they become so like you're just choosing 12 choose 3. There are 12 choose 3 ways to get this, and this are the same, and this are the same, so they're 12 choose 3. Okay, so again, if you haven't responded yet, like, is there any does can you say like how familiar you are with understanding just things in general about counting, or if there's anything in specific you want to go more about, or okay, so see a couple of people saying that they didn't understand stars and bars, so hopefully that clears it up. I'm like, does anyone still have any questions about anything in counting? And could you please, uh, and like, can you please show or just want to see anything you went over in this homework or anything? Well, we're going to continue on to the next slide then. So we're going to start talking about probability. So, um, so probability is very related to counting, and the reason why, like, let's just start with a small example. What's the probability of flipping heads with a fair coin? This isn't a trick question, just answer it. You can just answer it. So yeah, it's just 1/2. Okay, someone said, I think I would have trouble knowing when to use stars and bars and when to use normal combinations. Okay, so stars and bars does use combinations. So, okay, so you use combinations when you're choosing like one type of object from several. So I'm not sure if that made any sense, but like let's say we have 9 objects. If all of these objects are different, like if each of these has a different number on them, then uh, then you could use combinations to, for example, choose some of these to be part of one group. Like if we choose 4 of them to be in one group, and then we choose 2 of the rest to be in another group, then you would use combinations because you're choosing 4 of these, and then you're choosing 2 of these. But using stars and bars is only useful in problems when you don't know what these are, and you're just trying to find out the number of possibilities there are to find these. So, like I said before, these are you should only use stars and bars when the problem is equivalent to basically saying you have several numbers, like you have a bunch of numbers and you know what they add up to. So like let's say you know these add up to 15 and you want to find the number of solutions to this. And you can see that like combination problems where you use combinations don't apply to that because all of these objects are different, and instead of just adding them, you'd also have to choose. Okay. Anyway, back to probability. Uh, yeah, it's just 1/2 probability of flipping coin of heads and a fair coin. But why is that? Well, a fair coin means that heads and tails are the same chance. So the total number of ways that the coin can go is 2, and exactly one of those is a head, the other one is a tail. So you can see how that gives you 1/2 because every possibility has the same chance, and 1 out of 2 of them are good. So the probability that something happens is the ratio of the number of favorable outcomes to the total outcomes, assuming that every outcome has the same chance of happening. Sometimes it's easy to just count the number of favorable outcomes, like in the example above. There's just one of them, but otherwise, like probability is going to be deeply tied to counting techniques and how you can count. And just another notation that people sometimes use is that when you're considering the probability of something like A, they say P of A or P parentheses A. It's like P of heads on a coin toss is 1/2, and like P of like 6-sided die rolls 4 or 6 is going to be equal to 1/3. That's just a notation that people used. And like here's a more complex counting example using like a reminder of some of the counting techniques we used before. If I randomly selected an arrangement of the word algebra, what are the probability that the two A's will be adjacent? So people would like please try this problem. And actually, because it's about halfway through the class, if you want, yeah, we'll have a 5-minute break after this problem. But just yeah, so like just try and calculate this. Um, well, I'll give you a hint, which is the total in this case is going to be 7 factorial divided by 2, because you have 7 ways to order them, and you have to divide by 2 because that's it. What's a question? Okay, it's this question. So if I randomly select an arrangement of the word algebra, which means I randomly order the letters, what's the probability that the two A's are going to be adjacent and right next to each other? So the total number is going to be 7 factorial divided by 2 because you have 7 things to order and you have to divide by 2 since they're the same. Okay, well, the way you do this is, well, remember, you just have to count the number. You have to count the number of ways you can. Okay, I'll wait a second. So yeah, we're just choosing the number of ways that you can have the two A's be adjacent. Because they're the same, we could just imagine that we have one single letter, which is like for example, double A. I'm not sure. Like anyway, we're just representing it with one letter because they have to be adjacent. So then this is just going to be this is just going to be 6 factorial because you have to order these and then you can expand this into two ways. Like you're just treating the two ways as a single letter because they have to be adjacent. And then our answer would simply be 6 factorial divided by 7 factorial divided by 2, which is 2 times 6 factorial divided by 7 times 6 factorial. Again, remember this is 7 times 6 times 5 times 4 times 3 times 2 times 1. This is just 6 times 5 times 4 times 3 times 2 times 1. So these cancel and you get your answer, which is equal to 27 or 0.2857. But generally, people will just note. Generally, you will want to have instead of having uh, instead of having like a fraction, you generally want instead of having a decimal, you generally want a fraction. Anyway, we'll have a 5-minute break now, so we'll come back at 10:54 or 10:55. Alright, everyone, please turn your cameras back on. Because it's 10:55, so we're going to continue on to the next part of probability. So, next we're going to talk about dependent and independent events. We may have talked about this already in counting, but I don't. This is going to be just a quick refresher. So, if two events are independent, what that means is that the first one has no effect on the second one. So, an example would be if you what's the probability that I roll a die and it gives me a 1, and I roll a coin and it's heads. Clearly, if I roll a die, that doesn't affect the probability that my coin is going to be a head. So in that case, it's pretty easy to combine the probabilities, because we just have to multiply them. So there's clearly a 1/6 chance that I roll 1. There's a 1/2 chance I roll that I get a heads, and you multiply them, you get 1/12. And if you have two things, two events that are mutually exclusive, which means that if one happens, the other doesn't happen, then P of A or B is P of A plus P of B. So an example of that is, what's the probability that I roll a die and it equals either 3 or 6? It clearly can't be both 3 or 6. It clearly can't be both 3 and 6. So the probability that one of them happens is going to be 1/6, because that's the probability that you roll 3, and a 1/6 because that's the probability you roll 6, and you add them to get 1/3. So that's just one short example. And another important thing, like just the terminology that people use, is with replacement or without replacement. So what does that mean? Like probability problems, they'll often involve selecting objects from a pool. Like let's say, for example, I have a bag with like 30 blocks, and I am of 3 different colors, and I'm selecting 5 of them with replacement. So what does with replacement mean? Well, what that means is simply I put it back into the pool afterwards. So if I have, for example, 10 of each color, then after I take one out, the probability of getting one color is still the same because you put it back in. Alternatively, if it's with replacement, or I mean without replacement, what that means is that it just gets removed from the pool. So if I have 7, if I have if I instead say if I instead take a red, for example, if I take a red block, then the probability of getting another red goes down because now there's one less. I'm not sure if my explanation was good, but essentially, it's pretty straightforward. If there is replacement, you put it back after you choose it, and if it's without, then you just keep it out. So, so an example question, pretty simple, is what's the probability that a coin lands on heads and a 6-sided die lands on a 4 at the same time? So this isn't a very hard problem. So, this is pretty simple. All we're doing here is there's a 1/2 chance that it lands on a head, and there's a 1/6 chance that it lands on a 4, because again, uh, you have two possible outcomes for the coin. Exactly one of them is a head. You have 6 outcomes for the die. Exactly one of them is a 4, and these are independent, so you multiply them and you get your answer is 1/12. Does anyone have any questions about counting your probability so far? Like, please participate if you know how to do it, because then I will know that you understand the material. Are we going to need probability with NCR and NPR? So we will be using combinations and permutations to calculate some of the things, because we're going to need to. Like, for example, if as an example, if we're, I don't know how to explain this, but like if you're choosing some number of objects randomly, what's the chance that it's 3 objects or something like that? It doesn't, but like there will be probability problems that do involve combinations and permutations. So, like, next thing is compound events. What is a compound event? Like, a compound event is essentially you just have multiple things happening, and like in a series. And in order to calculate this, instead of calculating it as a whole, we calculate them at each step and then multiply them, or if we can. So, like for example, in the last case, I was technically using this because you roll the you flip the coin first. You have 1/2, and you roll the die, and you have 1/6. So here's an example: 4 green blocks and 3 red blocks are put in a bag and selected at random. What's the probability of selecting 2 red blocks if we're doing without replacement? What is this? So, without replacement. So, what's the what's the probability that the first one is a red block? Well, there are 3 red blocks and there are 7 total, and yeah, they're selected at random, so there's just a 3/7 chance. Is this in the slides? This is the slides. Not sure you mean. You still see the homework review? Um, is anyone else seeing that? I might have to reshare. Can other people say like what they see on the screen? Okay. Seems that okay. It seems that most people do see it. I'll stop and restart the share. Okay. I'll stop and restart the share to see if that helps. Okay, is it better now? Okay, well, I'll assume it is. So the probability here, if you choose the first red block, there's a 3/7 chance, and the chance for the second red block, well, I've started screen sharing. That's weird. Could you try and leave and rejoin? It might be that you're having like some internet issues. I'm not sure. Anyway, for the first one, there's a 3/7 chance. For the second one, for the second choice, now there are 6 blocks, but only 2 of them are red, so there's a 2/6 chance. And I know, like, one question that a lot of people have, for these kind of problems is like, well, isn't that not an independent event? But the answer to that is yes, it is. But we already know that the first one is red. Like the first one we choose is red. If the first one we chose is green, we can just discard it. So that doesn't really matter. So what we do know is that 3/7 chance, and then you have a 2/6 chance for the second one because it's without replacement, and you multiply these, and you get that this is equal to 1/7 because this is 1/3 and the threes cancel out. So does anyone have any questions about this? And I'll wait a bit for. Yeah. Sorry. So it's because it's without replacement. So at the start, you see there are 4 green and 3 red. Okay. At the start, there are 4 green and 3 red. If you take 1 red out, there are going to be 4 green and 2 red. And now the probability is 2/6. Do you see why? Like at this point? And by the way, if you just came back, can you please say in chat if you are able to see the probability basics now? Okay. Looks like most people are able to see it, so that's good. So as a reminder, 3 red and 4 green, so 7 total, 3/7 chance. You take 1 red out, there are 2 red and 4 green, there are 6 totals and 2 left. So number 4 is counting techniques. So another way you can go about using probability, doing probability problems, is to use counting techniques. So what does that mean? You can use combinations again. Wait, actually, I think there's another question on the last one. Can people try just in a private chat message tell me how can you try this problem? Again, you have 4 green blocks and 3 red blocks in a bag. This time you are choosing with replacement, meaning you're placing it back. And what's the probability you choose a green block and then a red block? Okay. Yeah. So it's just so yeah. This is just going to be 4/7 for the first green block, 3/7 for the red block, and you multiply these to get 12/49. So that one's pretty simple. Yeah. Um. Okay. So now we're going to talk about counting techniques. So what this means is we use stuff like combinations and permutations and or etc. So uh, in this case, it's possible. Like how do I say this? So for problems like this, it's often possible to try it directly. Yeah, hold on. It's possible to right. Sorry. It's possible to solve these problems directly by using counting techniques. Like for example, choose and stuff like that. So well, we're just multiplying, right? Because yeah. Remember the fundamental theorem of counting states that the number of possibilities for two things is equal to their product. So in this case, what's probably we choose two red blocks without replacement. Um, there are 7 choose 2 ways to choose 2 blocks from the bag, because we're just choosing 2 of these blocks, and this equals 21 of them, right? And out of these 21, 3 choose 2 of these are using one of the 3, have 2 of these red blocks, so that's equal to just 3. And this one is just becomes 3 divided by 21 equals 1/7. And yeah, like, does anyone have any questions about this? And everyone just try the second one. This time use counting techniques. So we're choosing a green block and then a red block. Remember, just look at the number of ways you have in total, and then how many ways you have to choose these. Why can't you do favorable divided by total is 3/7 divided by 2/6? You can. We did that in the last slide. But right now we're just showing another way you can go about doing the problem, which is to use counting techniques. So in this case, 7 choose 2 is 21, choose 2 is 3, and divide. So for this one, The number of ways you have to choose two blocks in general with replacement is just going to be 7 times 7 equals 49, which is 7 squared. And choosing a green block and then a red block, you have 4 choose 1 ways to choose a green block. You have 3 choose 1 ways to choose a red block. And you multiply them, you get 12. 12 divided by 49. And get that again. So does anyone have any questions about these probability basics so far? Because we're going to talk about another common type of probability problems now, which is which is card problems. So card problems, I don't think like they're it's just a name. It doesn't they don't often use like the same strategy, but it's just a name for problems that involve a deck of cards, and uh, it's just important to know like in competition math what are in a deck of cards and like how you can like choose from them. And so one note is that like okay, so deck of cards has 52 cards. There are 13 ranks, which are like levels or numbers, I think people say. Ace or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, and Queen and King. There are 4 suits: spades, clubs, hearts, and diamonds. Spades and clubs are black, hearts and diamonds are red. And because there's so many of these cards, it's a lot easier to, instead of treating them, yeah, it's often easier to treat these as compound events and not counting techniques. So, like, for example, if like, you shouldn't try to count like 52 choose 3 and 52 so choose 7 or whatever, because that's a lot of work. Instead, just look at compound events. So, what's the probability of selecting 2 aces from a standard shuffled deck without replacement? So, just try this problem. It's pretty similar to one of the problems you had before. So, this one, the number, so okay, remember, without replacement. So after you take a card, then you can't put it back. So probability of choosing the first ace is going to be 4 divided by 52 because there are 4 aces and 52 cards. And then we have 3 aces and 51. Then we have 3 aces left and we have 51 cards left. You multiply these, this equals 1. These cancel, actually. You got 1/13 times 1/17, and this is going to equal, I don't know this, well, 221 divided by 221, I believe. Someone put 3 divided by 663. Remember, you have to simplify that number, so divide both sides by 3. Someone put 12 divided by 52 squared. First of all, that's not simplified, and second of all, well, second of all, remember that we're using with replacement, without replacement, not with replacement. So after the first one, you end up with 51 cards left, not 50, not 52. Does anyone have any questions? Okay. Let me just check something. Right. So next we're going to just have some in-class problems. So I'll give you like 5 minutes to think about these problems. If you do not have any ideas like at all, please tell me because then I can try to help you. So yeah, just try these problems. If you have any questions, then please go and ask. Now, how do we do it if we don't know the ace is a spade or not? It's a red ace. So remember that spades and clubs are black, and diamonds and hearts are red. So automatically, it's not going to be red. It's automatically the first ace can't not be a spade. Okay. So for the first problem, what's the probability that the top card in the shuffle deck is a red ace and the second card is a spade? So in a deck of cards, there are only two red. There are only two aces. Two red aces, that is. So that's a 2 out of 52 chance. And the second is what's the probability that the second card is a spade? So here, I think I see a lot of people they're making a bit of small error. So there are 13 spades left in the deck, but there are not 52 cards in the deck now. There are 51 because one of them has been like sort of set aside for the other one. So yeah, like because we know the first one cannot be a spade. So 2 divided by 52, 13 divided by 51, we got this is equal to 1 divided by 102. So, does anyone have any questions about this problem? Uh, I'll just quickly go over the second problem as well. The three randomly selected positive integers, what is the probability that their sum is even? So, If you so there are a couple of ways you can do this problem. The first one, I think you can use a symmetric argument. So the probability that any one number is even is the same as the probability that any one number is odd. So if you have, for example, an odd plus an even, if you simply reverse these and you get an even plus odd, these probabilities are the same because, yeah, mm, uh, these probabilities are the same, but you can see that these add up to an odd number, these add up to an even number, and this is the case for all of them. You could just swap them. So then you can use a symmetrical argument to get that these equal to 1/2. Hold on. So another way you can do this is by like sort of just brute forcing it. Uh, well, yeah. So actually, never mind. This is a better way. So a sum is even. Like remember that two odds add up to an even. One even, and one odd add up to an odd, and so on. So sum is even. That implies there's 0 or 2 odd. The probability that there's 0 odd is 1/8 because you have 1/2 times 1/2 times 1/2. The probability there are 2 odd is going to be, well, 3 choose 2 out of 8, which is just 3/8. So 1/8, well, clearly both of these can't happen at the same time, so we can just add these. Remember, yeah. So yeah, sorry, none of these can't both happen at the same time. So you can add them to get the probability that one of them happens, which is simply going to be equal to 1/2. Um, okay. I see that some people they're using like stuff like 9 or like something divided by 9. Remember that even what that really means is just divisible by 2. So clearly there's the same number of there's the same chance you get an even number as that you get an odd number. Uh, yeah, I'm not sure. Like it's I'm not sure. Uh, like 0 is also an even number, so like 10. So I think that's a mistake that 0 by itself isn't positive, but 10 and 20 and 30 and so on are, and just one number isn't really enough to affect it in the long run because you have infinite numbers. Like if you just don't think of it as like base 10, you don't think of it as like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and you just think of it as even odd, even odd, even odd, you can clearly see how they're equal. So does anyone have any questions about anything from counting or probability? Uh, like, or like, does anyone not understand any specific parts? Like, I know people, as an example, some people had issues with stars and bars earlier. So, does anyone have any questions? Sure. The final answer is 1/2. It's 1/8 plus 3/8. There's a 1/8 chance that there are 0 evens and 0 odds, and there's a 3/8 chance there's 2 odds. And actually, this is another way you can see how it's symmetric because if it's 0 odds, there's the same. It's the same chance as there are 3 odds, which is going to be odd. This one is the same chance as having 1 odd. So those clearly have the same probability to have an even and odd. So so well, because it's 11:30, if anyone doesn't have any more questions, then you can leave the Zoom call. If you do, then you can stick around and ask.